So, thank you for the introduction. I'm Martien de Jong. I work at AMD here in Cologne. It's nice to be here, nice for the organization, thank you. As Artem said, I'm a hardcore backend engineer, and that's backend. I generate code for our NPU architecture. It's called AIE, Artificial Intelligence Engine, I think it is. Maybe there's another acronym, I don't know that. I'm on LLVM Discord, but I'm not there that often. If you have any question, here's my email address. Feel free to contact me afterwards. I'd like to get some traction on some of the issues that I will be presenting. So, short overview, I will go through some of the challenges that we have. There are quite a bit, but I will restrict myself to the ones that have impact on scheduling, instruction scheduling that is. I want to explain why we want to do things after register allocation. A lot of stuff in LLVM backend is done before register allocation, but our architecture really asks for the final scheduling stage just before going to the encoding. I will discuss some small but useful extensions that we have made in the course of the time, because the mainstream processors and backends, they do other things, and I needed to be able to break into that flow to do the things that we want to do. And finally, I will have some wishes where I would love to do them, but I don't have the time, and it has a lot of impact everywhere. But I may dream, I think. I have no page down here, but this will work. This will work. Yeah. Yeah. So the challenges. We have a 6-volt VLIW vector machine. So we have 2 load slots, we have 1 store slot, we have an ALU for the normal arithmetic and control stuff. We have a move slot, which is slightly more than just moving. I think everything that you can implement by wires and selectors is done in the move slot. And then there's the vector slot, which is focusing on multiply, accumulate basically of submatrices. So 2 by 8, 2 by 16. There are a number of different versions of the architecture that have different widths, different shapes, but mainly it's on smallish matrix multiplies. So we have 5 delay slots. So if you look at a conditional jump to somewhere, you have to fill in 5 knob cycles. You have to understand that this might be actually 6 instructions. So we have here 30 bits of instructions to fill at every branch. And you understand that we do our best to avoid branches. First of all, we have a rich set of selection, so that you can do a predicated computation of 2 values based on a condition without ever branching. Vector selections by element, and we have a hardware loop construct, which will give us true zero overhead loop. So you set up the loop and it will run for whatever you put in the loop counter. So, because we don't have interlocks on this architecture, we just pick up the value that is in the register at that point. It means that we need to fill out the cycle for the timing ourselves. So if we have a load which has a 7 cycle latency, we need to insert 6 knobs before we can pick up that result in the final instruction. So this needs to be exact. There's no way that you cannot schedule in this architecture. If you don't schedule, everything is wrong. Every single cycle will be missed probably somewhere. other than other VLIW architectures, we have a variable pipeline depth. So a load has 7 cycles, a multiply has 5 cycles, well, the vector multiply, this one has 2 cycles, this one has 1 cycle. And that means that every instruction may have conflict with other instructions that are issued in a different cycle. So you really need to look where are they using their resources, otherwise there will be a conflict. It will silently ignore one of your writes, for instance, and you're debugging forever to find where it went wrong. Yeah, well, so we have 2 load slots. We can only use them usefully if the loads come from 2 different memory banks. We have 1 linear address space, but it's separated in 4 contiguous memory banks. So if you want to schedule really optimally, you need to take those memory banks into account in your scheduling as well. That doesn't go wrong. It will serialize, but the entire processor will stall. So your 6 slots are doing nothing at such a point. Now, delay slot filling. If you look in the standard code generator, there is 1 delay slot filler, maybe 2. I think MIPS, Spark, maybe RISC-V, but they are talking about 1 or 2 scalar instructions. We have 5 of them, and we can't do that afterwards because we need to schedule an entire range of instructions across this thing. So what we do, we use a backward scheduling method. We say, well, we have a branch, it needs to sit at 5 cycles. In the scheduler, there is something like an exit SU. SU is for scheduling unit. I may say that a number of times. But this is marking the end of the basic block or the scheduling region in general. We put a latency of 5 in that. We schedule backwards and we know, oh, this should be at cycle 5. So we wait until it is available. Then we give it top priority to schedule it. So it will be the first one that gets scheduled so that we are sure that it will fit there. Luckily, it doesn't have any strange pipeline resources that it needs, so we are sure that it will fit at that first position that we encounter. Interblock scheduling. I've told you that I have a deep pipeline. So if I do a transfer to another basic block, I still have things that are extant in my pipeline. So they are going to do things, they are going to do resources, they may have some latency to the next basic block. And yeah, if we're here, we don't know exactly what is going on here. So we need to take that into account. Level 0 is just put in knobs at the maximum pipeline depth. Second level is that you look what is here, what kind of latencies could I have, and maybe you can reduce the number of knobs, but still it's far from optimal. So I guess I have explicit slide, oh yes. So what we do is we actually change the block order in which the scheduler is approaching the scheduler, and we use a bottom-up scheme over the control flow graph. So we do this, now we know the successor of that one, and since we now know what is in here, we can take that into account when scheduling that predecessor basic block. Here again, we have scheduled that one, we have scheduled that one. We take kind of the join of these two, and then we can schedule that one, taking both those blocks into account. That works pretty good in linear code, but of course, linear code is boring. Nothing happens in linear code. We have a loop, and now we are our own predecessor. All our major performance stuff is in this kind of loops. We have one block with code, because we try to avoid branching, so everything is with predicated execution there. But now you have the problem that we haven't scheduled our successor yet because we are our own successor. So what do we do then? We basically put the entire scheduling in a fixed point loop. So we start optimistically and say, there's nothing here. We are going to schedule, and then if we schedule, we check whether we are actually hitting resources or latencies that are there. If there is no conflict there, we're done. Then we have scheduled that block with the minimum safety margin that is possible. If not, then we go look what happened, how can we adjust that, and we basically stretch that safety margin one by one. And at the point where we are at the maximum safety level that we would have done otherwise, we will terminate, so we have a guarantee that we will converge to a solution. Now this was some time. This is, I'm talking about 1.5 years before we were at this one. But we needed to get better because that loop-aware scheduling is an approximation to what we actually want to do, which is pipelining. Now this is a simple loop. It does a load, it does an operation, and it does a store. And because of our load latency, we're mostly doing nothing. So we need to insert those 6 knobs, and we end up with a one-stage pipeline, as we call it, which has an initiation interval of 9. So we have these 9 instructions sitting in here, and every iteration takes 9 cycles. What we want, because we have this huge, big VLIW machine, is this. And don't worry, I will talk you through it. But this is what we now routinely generate. We have a one-cycle loop here. We have a big prologue. We have a big epilogue. And this is the consequence of not having interlocks. So those 8 R1 loads that you're seeing, they are just fed into the pipeline. So we feed the data into the processor pipeline, and they will end up in register at some point. And as long as that register is not written, you can pick up the previous value that was written in the register. So let's go down. So this R1 that is written is picked up here, and these ones are just preparing writing that register in later stages of the pipeline. This one then has its first use in the loop itself. On the other side, you see that this one is producing the last iteration in the loop will feed this add with its result. And the next one down will go around the loop once. So it will sit there, this loop will execute this cycle, and then at the next iteration, it is in the register, will be picked up. Now, and all these other values, they will go more and more and more around that loop. Oh, I forgot to delete something, but that is still there. So what we now have is we push 7 values in the pipeline, then we are ready to go. Then we run this loop in a single loop, so we have 1 cycle per iteration. There is of course some run-in time, some run-out time, but if you do 20 iterations, you are already gaining. Normally you would do hundreds of iterations in that inner loop. Why don't we do this before the register allocator? That's where the machine pipeliner lives. But if you look at it, this value is heavily overloaded because it can come from this one, from any of the other ones. So they are 8 SSA values glued together with phi nodes. If you know what the register allocator does with phi nodes, it tries to implement them using copies before starting any register allocation. And it will say, all those things are live across the entire loop. So I'm going to have 7 moves in this loop, and we are actually worse than a simple pipeline version that we have. So we tried that. There are some loops that can be pre-pipeline pretty good. They are usually longer, so they don't span more than 1 latency in that loop. But for the rest, this kind of work where we have 1, 2, 4 cycles of instructions, it just doesn't work. We get spills usually because it doesn't fit, or you get, like I said, a sequence of moves that implement a FIFO effectively in registers, and it will use more registers than you want and be wasteful. So this was also moved into that final stage of the scheduler, where we have perfect information about timing, so where we can do this stuff. And if you look at it, it's also pretty easy to do it at this point because they are exact copies of the instructions that we had in the original loop. We just copy them out into the prologue, we copy them out into the epilogue. We don't need to modify any register, renaming, whatever. It's just, it follows directly from the linear schedule that we make, that we wrap around that one cycle. So let's discuss some of the extensions that we made together. As I said, it's 2 years in the making. I tried to fit it in 20 minutes, but there will be things I have not listed here. One thing of not having any interlocks and having variable pipelines or variable pipeline depth for different instruction is something that we can see here. We have this instruction, which is logically before that one. It does a write back. It will have an output dependence with the write back of this instruction. But since this one has a way longer latency than this one, we can actually issue this 2 cycles before its logical successor, predecessor. So if you then count, you get to, I'm writing back in stage 1, 2, 3, 4, 5. I'm writing back in stage 1, 2. And then you subtract them and you subtract one more, you get to a latency of -2 that you can do. Now, for a typical list scheduler, I think we've all seen list schedulers in action. You would go through your dependency graph, and once you have scheduled something, you know you are at that cycle, and you bump your scoreboard to that cycle. In this case, we cannot do it because we want to insert it back. We don't want it in the current cycle that we are when we have scheduled this one. We want to schedule it earlier. So that was one of the bigger changes, that we, first of all, get this negative latency in. No one had thought that someone would need it, so it was coded as an unsigned in the scheduling dependency. If it is unsigned, then you're using sentinel values that are way out of range, but those were just the values that we wanted to represent, so we couldn't use those sentinels, so we moved those interfaces to standard optional. I can better read it here. Yeah, and indeed to make the scoreboard in such a way that we can move 2 cycles. So at every scheduling insertion, we got delta cycles, as we call it. So it's not at the current cycle, but it's 2 cycles ahead or earlier. We can also go the other way, but that's. So that was one that we needed to do. We have a complicated model with many resources and many latencies, and we only wanted to code it once. So we have the machine pipeliner and we have the machine scheduler, and they internally use a different representation. So we unified that in what we call the resource scoreboard. The resource cycle is reused by the pipeliner and the post scheduler. And since that is an arbitrary thing, you can do arbitrary codings of what conflicts you want to recognize there. So we have 4. Of course, we have the slots because we want to fill slots as much as possible. Then there are the resources, which are the read ports, the write ports, the memory interfaces that we need to access in particular cycles. And then we added this is reasonably standard, but we needed to do more because we wanted to represent those memory bank things. So we want to know whether two loads or stores are in the same or in different memory banks. This one is used to make sure that they are in different memory banks so that we can put them in parallel. This one is mainly saying that we are in the same. So this comes from an explicit memory bank annotation. This one comes from the normal alias analysis, which says these may alias, then we assume that it is the same. And we have some more view on that so that we really know that it is the same bank, and then we just say, okay, they're the same bank, we're going to draw a cycle here so we can better schedule them in separate cycles and maybe fill both cycles a bit more. This is something that I would have expected from a retargetable compiler framework, but it wasn't there, so we added it. That's basically the rigging that you need to do something on a function scope. The standard machine scheduler just goes through the basic block from bottom to top, and at some point here it calls schedule. So we needed to do that bottom-up phase. We need to iterate until we converge. So that's where we have the next block. In enter function, we set up the function-wide scope. So we allocate space to put our actual schedules in before we are materializing them. And then, enter block. We switch our context to the new block, look at our predecessors, look at our successors, these kind of things. And we set up those glued scoreboards and dependency class. It's very little thing. They are just 5 or 6 virtual functions that we add to the standard scheduler class, but they are so important to get right if you don't want to drown in the logic. It's complicated as it is already. I know that the AMD GPU backend, it just collects everything in the normal scheduling stuff, and then in a function close to this one, it says, okay, now we start the function-wide scheduling. So it's just totally turned the scheduling logic inside out. That's about it. Yes. If you look at what I've been talking about, you see that we are going interblock scheduling. So we are combining the instructions from different basic blocks. The standard, this is the base class of all schedulers in LLVM. And that base class was maintaining maps from instructions, was using the basic block iterators to make the traversals. You can imagine that if you have a basic block, you have the instructions in a particular order to build the dependencies. You traverse them, usually backwards. You see what they do and you connect them up with dependencies. Oh, I'm reading this register, he is writing that register. There's a true dependence between them. If you then use those iterators, but those iterators come from different basic blocks, they are non-compatible anymore. So that didn't work. So we have detached the scheduling DAG instruction from the notion of a basic block iterator, because we already have this array of scheduling units that represents the original order in which we want to schedule. So that's just a kind of an abstraction on what we are scheduling. We have detached it from the actual basic block notion. In pipelining, we use that to create the loop carry dependencies. So we have one iteration of the loop and then a copy of that iteration as the second iteration. We go just linearly through all the scheduling units, and what we build across this boundary, they are the loop carried dependencies that we need. So that's input to the pipelining algorithm that needs to know that it doesn't stretch it too wide and maintains all those loop carried dependencies correctly with their latencies and their resource usage. Yes. Now this is a colleague of mine said, no, don't show this, but this is just recent. But this is actually the normal flow. This is pre-pipelining. That's where ARM does the pre-pipelining. Then we go to file elimination and register allocation. And then finally there is scheduling and pipelining. So this is where most of our work is, and we have recently expanded that to get rid of those physical register dependencies, which is usually for post schedulers, that's where you get killed. You get a register dependence because the register allocator didn't see that you needed that register in multiple stages of that loop, and that's generating a conflict, and you can't pipeline that loop because you get a very long cycle across the loop. So what we do there is we look at all the live ranges within the loop. We make virtual registers again. We then generate that scheduling DAG. We do the modulo scheduling, and afterwards we try to find, based on what we have scheduled, a new register allocation. And then we can fail and try again with another register allocation or with another heuristic scheduling heuristic. But yeah, the fact is that we just introduce these virtual registers totally at the end of the code generator pipeline. Some of the infrastructure wasn't up to it. So yeah, virtual registers, if you would find them, you would normally say, oh, we are in SSA mode, and then we don't need anti-dependencies. We do need anti-dependencies because we are far further in the flow, and we really need to take care of them. So those were a few. Yeah, they are not big changes, but we had to change them upstream to be able to put our code generator model into the structure. Now then I have some future wishes. There are a few things which are very ugly, and I would love to clean them up. One thing is that we are doing iterative work, and we do it in two modes. So we have the physical dependency graph, so with all the physical registers, and we have the virtualized DAG, so where we have selected live ranges virtualized to be reallocated at some point. Those guys are invariant over anything that we do. The dependency graph will really stay the same. It's just that we want to run different schedulers on them. These need to iterate because we generally go from the minimum initiation interval, so the number of cycles in the loop, to a maximum, and we want to find the first one that is there. But schedule DAG inster is the scheduler, and it doesn't have any copy constructors, and it will schedule on its own instance record. So there's no way to pass in another schedule DAG like this. Sorry, where are we? Here. So we want to schedule on the physical DAG, and we want to schedule on the virtualized DAG, but this schedule is a method of the DAG itself. So it's difficult. I want to cut that loose, but there are so many things that know about the internals of that one. They are all public data members, and everybody is touching them and looking at them. So if you want to change that, you have to go through all the code generators in the tree and fix them. And I don't get the budget to to do that. But if someone is interested in doing some put in some elbow grease, then I would be very happy. I think this concludes my talk. Can I take questions? Yep. Good. Are there any questions?
Thank you, Martien. That was really nice of you. And if there's any questions, you can ask right now, and I will happily repeat it to the microphone so that it's actually on the recording as well. Give it to you.
Yeah, thank you. Does it make sense, or would it actually make sense to like replace the scheduler DAG inster with like custom implementation at this point, than just trying to like?
If I would do it again, I would probably. We've also untangled some of the hierarchies that are in there, because there are strange hierarchies in that schedule DAG. If you look at the core of the schedule, there are a few things in there which are used, but they are mostly used by other companies. But we would have another scheduler. And as I said, there are already, there is the pre-scheduler, there is the post-scheduler, there is the scheduler that runs on selection DAG nodes. So that's why we have S units and not something else, because those S units, they can also refer to scheduling DAG nodes. They can refer to basic blocks in some other kind of scheduler. You have them with register pressure tracking for before the register allocator, without them. I started working with LLVM 2 years back, and I didn't know all these nooks and crannies of what went wrong. But if I would do it now, I would definitely make a clean cut and start with it. But sadly, that's always after you've done the work, and then no one is interested anymore. It works, doesn't it?
Thank you. Yeah, fair enough. Are there any other questions? Maybe from the audience? No? Okay. Then, thank you, Martien.
Thank you.